All right, welcome to Tollefson Physics. So what we're going to talk about today is kinetic energy and how we get that. All right, so kinetic energy is motion. It's the energy of motion. Anything that's moving has kinetic energy. All right, so we're going to look at a situation that we've looked at before where we have somebody standing on top of a building dropping a ball. But we're going to go back to the situation where we're only going to look at the ball, because actually what I'm going to try to do is figure out how do I calculate kinetic energy. All right, and there's a little bit of a trick to figuring this one out. So, well, let's ask our questions like we did before. So basically, gravitational potential energy is not part of this if the system is only the ball. The Earth is outside the system, right? Earth is not inside my system, which tells me I'm probably going to do work at some point because of Earth's gravity, right? We talked about that before. So what's going to happen is the height's going to change, it's going to speed up, and so it's going to convert all of that energy to kinetic energy. So when I do something like that, I have no initial energy, but I'm adding work due to the gravitational system of the Earth. And that will equal the final energy, which in this case is kinetic energy. Okay, well, that's interesting. So how do I get somewhere with that? How do I figure out what that is? If it has something to do with motion, I want to know the velocity. I want to know how fast it's moving. All right, so once again, work is force times a distance. All right, well, what is a force that causes something to move? Well, let's think about Newton's second law, right? F net equals ma. So let's try that. Let's put that in for our force. So work equals force times mass times acceleration. Okay. All right. Oops, I made a mistake. I substituted in force, and it's mass times acceleration times distance. All right. So we've got something there. What can I, where can I go? What can I substitute in there? I don't know time. I don't know. So if you remember way back, kinematics equation, there was this equation that doesn't have time in it, but it has acceleration and it happens to have distance in it. Could I use that to help me out? Well, the answer is I can. Because notice this, AD, AD. Well, what if I solve for AD here? So to solve for AD, what I have to do is I got to move this to the other side. So VF squared minus V naught squared. Divide by 2, because there's that 2, and that will equal AD. Okay, cool. So now I'm going to put that into this equation. Now, we're actually only interested in the final velocity, because what was the initial velocity? It was 0. So actually this goes away. This goes to 0. So let's substitute that in. So work equals, and I'm going to put the half in front, m, the v final is what's left, squared. And that equals kinetic energy. This is the equation you see in most textbooks, that the kinetic energy equals 1/2 the mass times the velocity squared. So we can use that to be able to predict things like, oh, how fast is that ball when it hits the ground? All right, let's do a real simple example of calculating kinetic energy. And so let's just have a car, right? We got a car. Let's just make it a nice old 1,000 kilogram car, and it's traveling about 60 miles per hour, which is approximately 25 meters per second. So we're just going to apply what we just learned about calculating kinetic energy. And so kinetic energy equals 1/2 the mass times the velocity squared. And so all I'm going to do is plug in these numbers in this particular case. So 1,000 kilograms, 25 meters per second, and I'm going to square that. So let's grab our handy dandy calculator and go 0.5 times 1,000 times 25 squared, and we get a value that's quite large. So 312,500 comma goes there, so 312,500 joules. So that's just from its motion. Now, what you'll see in future is that we're going to use information where we can actually do something a little more interesting and transfer energy from one mode to another, and to be able to make some interesting predictions and calculations regarding that. All right, so the only way to learn physics is to do physics. So here's an example problem that you can do based upon the roller coaster that we've been looking at. And so if we have the same 1,000 kilogram roller coaster at 100 meters above the ground, we're going to say that it starts with no velocity and everything else is gravity fed. So if it's gravity fed, what's going to happen is the speed of the roller coaster when it gets to the ground level is going to be 44.72 meters per second. At the top of the next loop, it's going to be going 20 meters per second. And at the top of the next hill, it's going to be going 38.73 meters per second. So what I want you to do is I want you to calculate the kinetic energy at each of those locations. Now hit pause here to give yourself time to do that, and unpause when you're ready to see the solutions. All right, so kinetic energy is 1/2 mass times the velocity squared. And so what you're going to take in each of these cases is 1/2 times 1,000 kilograms multiplied by the speed. And so for the first one at the ground level, the speed is 44.72 meters per second. And so you square that. Don't forget to square that. That's a common mistake. And so when you do that, it equals approximately 1 million joules. So I rounded the number here, but it's approximately 1 million joules. So we do the same thing for the other one. So for the top of the next loop, the speed is 20. So I put 20, square it, and I'm getting 200,000 joules is the kinetic energy at that point. And then at the top of the last hill, then if you use 38.73, the kinetic energy rounds to 750,000 joules. All right, so hopefully that helps, and keep on practicing.